Hello, check. What's going on, everyone? Welcome to Vedantu JEE English. My name is Pahul. If I am audible and visible, please write here in the chat box. You know the drill. So, today, what we are going to do is something that's extremely important for all of you who want to better your organic chemistry. And today's class is going to be beneficial for those of you who are here for revision, especially for reaction mechanisms. What reaction mechanisms? SN1, SN2, E1, E2, E1CB. And apart from that, a few reaction mechanisms that are more important from the alkyl halides chapter, haloalkanes, haloarenes chapter. Alright. So the thing is, if you are someone who has not studied these chapters at all, then my suggestion is that you take it slow, think about the long-term benefits of studying these chapters thoroughly, and go through the classes of these chapters one by one. The links of those classes are given in the description box down below. English classes, my classes, okay? But if you have some idea of these chapters and you want to make your knowledge better, if you want to revise these ideas, then today's class is going to be really helpful for you. First part. The second thing is that today's class is sort of like a part 1 because the part 2 will be next week, okay, on Wednesday, where I will discuss previous year questions of reaction mechanisms and alkyl halides. So today we'll revise the reactions. I'll give you a couple of questions here and there, but problem solving centric session will be next week on Wednesday. Alrighty, chalo. Are you ready for this? So the first reaction mechanism that we are going to discuss is my favorite, one of my favorite reaction mechanisms. We are talking about the SN2 reaction mechanism. Now, what does SN2 stand for, people? What do we mean by SN2? The S stands for substitution. Yes. N stands for nucleophilic. And this 2 stands for bimolecular. Alright. So what happens over here is we have a substrate in which there is a very nice leaving group. Let me draw something for you. So we have a carbon in the middle. Let's say around this carbon we have 3 hydrogens and one group is the leaving group. So I'm going to draw it something like this. Okay. I'm going to draw it something like this. I will draw the wedge dash kind of a structure for this. Alright. And now let's say 3 of these things are hydrogens and one of these is a leaving group. So let's put hydrogen, 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 and let's say the leaving group is chlorine in this instance. Fine. Now what happens is when this is approached by a strong nucleophile, very important for you to remember that in SN2 reaction mechanisms, we need a strong nucleophile. A strong nucleophile will generally have a negative charge on it. It will not be a neutral species. Alright, so let me put this point over here. You need a strong nucleophile. Okay, one very good example of a strong nucleophile is OH negative. Yeah, you take NaOH, KOH. It will provide you with OH negative ions. OH negative ions are extremely reactive. If they do not have any acidic hydrogens to capture, then they will act as nucleophiles. Can you guys tell me what's the difference between a base and a nucleophile? Can you tell me what's the difference between a base and a nucleophile? What's the difference? See, the difference is that in a base, whenever you act as a base, whenever a chemical acts as a base, it wants to capture a proton. Alright? But whenever something acts as a nucleophile, in the language of organic chemistry, that means that you are trying to capture a carbon with a positive charge or a carbon with a positive character. What do we mean by carbon with a positive character? It means that carbon is associated with something that's electronegative, which is pulling electrons toward itself, rendering carbon with a positive character. So the nucleophile nature is when you attack a carbon Basic nature is when you attack a proton. Now protons are very small, they are very easy to capture. So acid-base reactions are very quick. Whenever you have to capture an H positive, it's very quick. But if you can't capture an H positive, then nucleophilic reactions are slower. The environment has a huge impact on the speed of nucleophilic reactions and the possibility whether the nucleophilic attack can happen or not. For instance, over here, you have an OH negative. This chlorine that we have, chlorine is a huge element. It's a big atom, yes. Now chlorine has its own electron cloud as well. So can I say that it will have its own electric field over here? Yeah, let's say this is the electric field of chlorine. Cool. Now if OH negative wants to approach this carbon, do you realize that OH negative cannot approach from this side? Yeah, if OH negative tries to come from here, it's not possible for OH negative to approach from these sides because chlorine's electric field will repel the OH negative. So the only possible place of attack over here is if my OH negative approaches from this side. Yes. And what kind of an attack is this? We can call this a backside attack. Backside attack only. And as OH negative attacks this carbon, at the same time, simultaneously, this chlorine will also leave. So OH negative is attacking, the carbon can't hold 5 bonds at a time, obviously. So chlorine has to remove itself from the system. Yes. This is how an SN2 reaction happens. Now, after this thing happens, what will be formed? You won't have a chlorine, you will have an OH group. That's all. Cool. As simple as that. Johan is asking, how does carbon have a positive charge? It does not have a positive charge over here. It has a positive character. How does carbon have a positive character? If carbon is bonded with chlorine, chlorine is high in electronegativity, so chlorine will have a partial negative character. Carbon is lesser in electronegativity compared to chlorine, so this will have a partial positive character. And this partial positive character is responsible for attracting the OH negative towards it. As simple as that. Now people, let's try to visualize what will happen while the reaction is going on. When the reaction is happening, what does this look like? Let's try to think about that. So a bond between this carbon and oxygen will be forming. Yes, I'll say that this bond is forming right now. And at the same time, this bond is breaking apart. So what I've done is I've made dotted lines to signify that this bond is under the process of formation and this bond is under the process of getting broken apart. And at the same time, the 3 hydrogens, where would they be now? That's the interesting bit over here. The hydrogens that we had made are all in this one plane now. There's a hydrogen over here, there was a hydrogen over here, okay, and there's another hydrogen right behind it. And if this is difficult for you to imagine, I have brought models for you. This is what this entire picture looks like. Okay, I'll zoom in the camera a little so that you can see that model easily. Now can you see the model better? Yeah. So you can imagine that this is the bond that is getting formed, this is the bond that is getting broken, and the hydrogens are all in the center right now. Yeah, this is while the process is going on. The reaction is happening right now. So this bond is getting formed, this bond is getting broken, and the hydrogens are all in the center. You can see that fan of hydrogens, right? Nice. So I'm going to zoom it out. Back to the regular view of the screen. Just let me check the focus as well. Cool. All right. So my dear friends, this particular picture that we've drawn over here, this is while the reaction is happening, this is known as a transition state. Okay, transition state. Now to isolate this particular state in the laboratory is not possible. It's an unstable state, highly energetic state. We've provided the energy for the reaction to happen, and then it reaches this particular state and then finally goes down to making the products. So this transition state is something that we can imagine. It is pretty obvious to us what's going on over here in the transition state, but we can't isolate this in the laboratory. We can't take this particular structure out of the reaction mixture and say, oh, look at the transition. You can't. This is something that you have to imagine logically. All right. And once the transition state is done, after the transition state is over, now you'll have a new compound. You'll have OH, 3 hydrogens, okay, cool, and a Cl negative has left. Very nice. Cool. All good. So this is a broad idea of what an SN2 reaction is like. Now there are a few more points of SN2 reactions that I would want you to note down. Okay. And before we note down those ideas, let me remind you that at Vedantu we have a lot of things for your benefit that are actually available for you for free. So one of those things is this Vedantu daily practice problems. Link is in the description. So it's like a test series kind of thing, and you get tests daily, so you can attempt those. Links are in the description box. Make sure you check them out. If not now, then after the class, whatever. ठीक है? बढ़िया. You'll get a good number of questions over here. Nice. So first of all, let's talk about the energetics of the reaction. This is a diagram of the energetics of the reaction. On the y-axis you have energy, potential energy you can say. On the x-axis you have the progress of the reaction. So we started with the reactants, Rx, X is your leaving group, which was chlorine in our example. And what happens is you provide it energy to reach the transition state. In the transition state you can see that there's a bond that's being formed and there's a bond that's being broken. And ultimately once you reach the product, now your carbon chains are always denoted with R. In organic chemistry, carbon chains are denoted with the letter R. So R is now bonded to the nucleophile, and at this side you have your leaving group that has left, Cl negative. Cool. Pretty nice. Now my dear friends, Dinesh has brought up the point of Walden inversion. Let me try to show you what that looks like in the diagrams over here. So let's do one thing. Let's take a very simple substrate like we were, nothing fancy over here. Let's say we have this, let me think, where do we do our attack from? What will be easy for you to visualize is what I'm thinking. Yeah. So let's do one thing. Let's put the leaving group over here. Let's do it this way. So there's a hydrogen now, and these two groups I'll take different groups over here. So let's say this one is another CH3 and this is, let's say, deuterium. Okay. D stands for deuterium, which is an isomer of hydrogen. Not isomer, isotope of hydrogen. Yeah. Now let's attack the OH negative on this particular carbon. My dear friends, do you notice that this carbon is actually a chiral carbon? 4 different substituents on a tetrahedral carbon means that the carbon is chiral in nature right now. It is optically active in nature right now. What will happen when I attack the OH from the backside? Just try to visualize what's going to happen. This is what we have right now. Hydrogen, deuterium, and your CH3. It's like a fan. Yeah. And the OH is attacking from here. What happens is the chlorine will leave away. OH attacks. This fan flattens out in the transition state, and the fan then turns into the other direction. It's like an umbrella flip. If you take out your umbrella when it's super windy and the wind just blows into your umbrella and turns it upside down, yeah, something very similar is going to happen over here. Let's try to draw the final product and it will be even more clear to you after that. So this is the carbon. And now the OH group is over here. Plus, of course, you have your Cl negative. Can you see the difference between these two? Can you see that the umbrella of hydrogen, deuterium and CH3 has now flipped? Can you see? Deuterium was pointing in this direction, now it's pointing in the other direction. CH3 was pointing here, now CH3 is pointing here. This umbrella flip that has happened in the structure, this flip is also known as a Walden inversion. Alright, this is known as a Walden inversion. You can also call it the inversion of a stereocenter. Alright, cool, pretty good. This is all about SN2 reactions, people. So just a few more points that you can revise about SN2 reactions. It is a single step reaction, alright. The rate law is basically equal to rate constant into the concentration of the substrate, that is the alkyl halide that we've taken, into the concentration of the nucleophile. So if you take more OH negative, rate of the reaction will become higher, speed of the reaction will become higher. If you take more carbon with chlorine, if you take more of the substrate, rate will become higher. Order of the reaction is 2. What is order of the reaction? Order of the reaction is basically the powers in the rate law. So over here, if you've revised chemical kinetics with Novamita ma'am, I'm sure, then you would know that the powers over here are 1 and 1. So 1 plus 1 is 2. That's the order of the reaction. Now, how many molecules are getting associated with each other in the slowest step of the reaction? The good thing is that over here there's just one step. This is a single step reaction. So in this particular reaction, you've realized already that 2 molecules are attacking each other. Yeah, these 2 are colliding with each other and then the reaction is happening. So the number of molecules colliding inside an elementary reaction is known as the molecularity, and that over here is 2. Okay? Then the nucleophile attacks from the backside. We've understood this in the beginning itself. And there is always a complete inversion of configuration, which is also known as Walden inversion. We've understood all these points about SN2 reactions. And there are multiple SN2 reactions that you will encounter in organic chemistry throughout. Some of them I will share with you today. A lot of them I will discuss with you in the upcoming classes. We'll do a bunch of questions on Wednesday when I have the previous year question class of this particular chapter. You'll realize how important all these pieces of information are for us. Okay? Harithanam is saying if there's no flip, it's called retention, right? Yes, you're absolutely correct. If the flip happens, then inversion. If the flip doesn't happen, it's called retention. Now, the thing is that you need space for such reactions to occur. Okay? If there is no space for the nucleophile to approach, then the reaction will not happen. We'll see those examples in a minute. Let me see, there are more points to this reaction. There you go. We'll read point 7 at the end, okay? Let's look at point 8. Polar aprotic solvents like dimethyl sulfoxide, dimethyl formamide, acetone, these favor the SN2 reaction. Okay? So polar aprotic solvents are useful for SN2 reactions. Fine? Keep that in your mind. Dimethyl sulfoxide, dimethyl formamide, do you remember the structures of these? If you don't remember, then make sure you revise them. Dimethyl sulfoxide, dimethyl formamide, acetone, I'm sure you know this at least. So, strong nucleophiles favor SN2 reactions, we've already understood this. What about the nucleophilic strength? We are talking about aprotic solvents. Aprotic solvents do not solvate your species inside it. If you dissolve something in water, water will solvate it. You remember we talked about the question of basicity of amines in the class on Tuesday. Yeah. So over there, what was happening? Water was solvating the amines. But in polar aprotic solvents, solvation doesn't happen, right? So in polar aprotic solvents, F negative is the strongest nucleophile. But what happens in water is that water will solvate your fluoride ion. Water will solvate Cl negative ion, Br negative ion, I negative ion. Yes. So in water, fluorine will be highly solvated and therefore this will not be able to act as a nucleophile. So just a revision for you that in polar protic solvents, more solvation of fluoride means it's less nucleophilic, but in aprotic solvents, where solvation is not something that's going to happen, smaller ions with higher charge density are better nucleophiles. Okay. And then you have the reactivity of the substrate. This is what you were asking about, right? So, smaller substrates are more reactive. What do we mean by smaller substrates? We basically don't need a crowd over there. If you have a carbon with just hydrogens on it, yeah, and this is, let's say, the leaving group, your nucleophile can very easily approach over here because there's no crowd. But instead of hydrogens, now let's say you have bigger groups over here. Let's say you have 3 CH3s. Now do you see how much crowd there is? Can you see how much crowd there is? There's so many electric fields that are going to stop this nucleophile from approaching. And therefore, in this particular case, because of steric hindrance, you understand the meaning of the word steric hindrance? Steric hindrance means that there's not enough space, there's a lot of crowd. Yeah. So because of the crowd, the nucleophile will not be able to approach. So that's why the reactivity order is as such. Methyl halides are very reactive towards SN2 reactions. Then you've got 1 degree halides, 2 degree halides, and 3 degree halides are not reactive at all. 3 degree halides do not undergo SN2 reactions. If you take a 3 degree halide, try to do an SN2 reaction with it, it doesn't happen. E2 reaction happens instead. We'll see E2 reactions in a while. Okay? Chalo. So people, I think this is enough information about SN2 reactions. Just read the point number 7. If the substrate is dextrorotatory, it does not mean that the product will be levorotatory. So dextrorotatory and levorotatory are something that we verify in the laboratory itself. The optical rotation of any compound cannot be predicted. You have to go to the laboratory, put it inside the, what do you call it? I forgot the name of that instrument. Optical, where you measure the optical rotation. You have to measure the optical rotation of the polarimeter, yes. So you have to put it into the polarimeter and then you have to check the optical rotation of whatever sample you have. So you can't predict the optical rotation of anything. Okay? Cool. So that's it. So tell me, which of the following compounds will not give an SN2 reaction? Which of the following compounds will not show you an SN2 reaction? What do you think? Very simple question. Sinan, did just see the name of this channel. This is called Vedantu JEE English. We have another channel called Vedantu JEE, which is in Hindi. So I take classes there separately, I take classes here separately. So if you want to learn from me in Hindi, there is a different channel for that, yeah? So, see, this is a 3 degree. Yeah. This is also 3 degree. So these will not undergo SN2 reactions for sure. What about option B? Can a nucleophile attack over here? My dear friends, such a species, okay, this is a very special case that you have to remember. Such a species is known as a vinylic species or a vinyl species. You can call this a vinyl chloride, okay. Now in vinyl species, what's happening is this particular carbon has a double bond with this carbon over here and then a chlorine on the right hand side. This particular carbon is not reactive towards SN2. Okay, this is not reactive towards SN2. Same thing is happening over here. This type of a species is known as a phenyl species. You can call this a phenyl bromide. Again, the same thing. This is an sp2 carbon. This is already a planar carbon. How will you make a transition state out of a carbon that is already planar? Yeah, you wanted the hydrogens to flip, right? How can a double bond flip? How can you flip a double bond? You can't. So, it's experimentally observed that phenyl and vinyl species do not undergo SN2 reactions. So, all the species that are mentioned on this page, none of them will go through an SN2 reaction. Keep this in your mind. Phenyl species and vinyl species. Whenever you have a C double bond and you have a leaving group on the double bond. Cool. Haritanam, they might not ask this in the board examinations, but you never know, man. It's not that complicated either. Okay. Standard cases. Now that I've told you, I'm sure you can easily predict. Tell me this one. Which of the following will give an SN2 reaction? Which of the following are good for an SN2 reaction? Tell me, people. This is vinylic. Already seen, this will not give you a reaction. This is 3 degree, but this will not give an SN2 reaction. What about this? This one, okay, this type of a species is known as a benzilic species. Benzilic species are really good for SN2 reactions. Okay, these are great for SN2 reactions. Fine. All right. So this will give you a reaction. Why is it great for SN2? I'll tell you in a while. What about this one? This is also 3 degree, right? 1 carbon, 2 carbon, 3 carbons, and then the leaving group. So this is also a 3 degree. Therefore, this will also not be a good idea for the SN2 reaction. Now in the benzilic species, let me remind you once again what the transition state looks like. This is the carbon. This is whatever the planar thing on it. This is where a bond is getting broken. This is where a bond is getting formed, right? Now think about these bonds that are getting broken and formed. Can you imagine that carbon has basically a p orbital, and in that p orbital one side is getting broken apart, yeah, chlorine's side is getting broken and the nucleophile's side is now getting overlapped. There's a p orbital, nucleophile is overlapping with it, then chlorine is leaving at the same time. Now this particular p orbital can be resonance stabilized with the benzene ring over here. Okay? This benzene ring that is here, that can stabilize this particular. Got it? So because the orbital can get resonance stabilized by these particular p orbitals, benzilic species are really good for SN2 reactions. Okay? So please keep this in your mind. A very similar species to benzilic is known as the alilic species. Okay. So this carbon over here is very good for SN2. This type of a species, can you see the similarity? Carbon which is next to a resonating structure, carbon which is next to a double bond. Okay. So such species are known as alilic species. Allyl or allylic, whatever you want to call them. So allylic and benzilic species are great for SN2 reactions. Perfect. So people, let me remind you, if you guys want to learn organic chemistry from me from the very basics, see right now I'm rushing through things because this is more of a revision class because we're very close to the examination. But in case you want to learn from the very basics, you're targeting the second attempt and not just the first attempt, or maybe you're in 11th class right now, then you can either search for Epic GOC on YouTube. Just search for Epic GOC, you'll see a playlist with my face on it. If you attend the lectures of Epic GOC, 10 lectures, you'll become an expert in general organic chemistry. Even isomerism is included in this. Optical isomerism confirms everything. And the other thing that you can do is check out the playlist in the description box down below. Full classes playlists are given in the description box down below. So the entire reaction mechanism playlist, the entire alkyl halide playlist, I have given that to you in the description box down below. Classes are in English, so don't worry about that. Fine. Now my dear friends, the next reaction that we have is the SN1 reaction. Substitution nucleophilic unimolecular. Unimolecular. That's the interesting part over here. So what we will have is a substrate that's kind of similar. Okay, we'll have a substrate that is kind of similar to your SN2 reactions. Okay, but the reaction conditions will be slightly different over here now. So let me take this specific substrate. Something like this. There is, let's say, a CH3 on this one, and there is a CH3 going at the back. So my dear friends, do you realize that this carbon at the middle now is a 3-degree carbon? So on 3 degrees, your SN2 attack cannot happen. So what happens over here is, if we provide this a little bit of heat, a little bit of energy, what happens is, leaving group just leaves. If you provide a little bit of energy, the leaving group will just leave. And what will get formed is something very interesting. You have this carbon at the center, right? You have a CH3 on it, which is at the left hand side. CH2D, there is a CH3, and there is another CH2CH3. Bromine is at the side now. This particular carbon will have a positive charge on it. What have you formed over here? You formed a carbocation. Alright. What we have formed over here by taking out the leaving group is a carbocation. And the interesting thing about carbocations is that carbocations are planar in nature. Yes, carbocations are all planar, sp2 hybrid. Now, the next thing that we do, what we do now is we put a weak nucleophile over here. In SN2 reactions, we were putting strong nucleophiles because over there you had to take the nucleophile and use the strength of the nucleophile to attack the substrate. But over here you don't need the strength of the nucleophile at all. SN2 reaction over here cannot happen. So you have to let this break apart, make a charged species, and then attack it with something that's mild. Something that will attack only if it has a charged species to attack on. weak nucleophile. Now, my dear friends, before I tell you some examples of weak nucleophiles, charged species, what kind of a medium should we have to stabilize a charged species? Charged species are stable in polar media. So if you take a solvent like water, very nice. So we'll try to take a polar protic solvent over here. Water, for instance. This reaction can happen easily in water. And then weak nucleophile, water itself can act as a weak nucleophile. OH negative is a charged species. It will attack faster. Water is just present over there. Water is like, okay, now that I see this positive charge, now I can attack. So this water can attack the positive charge. And you realize the attack can happen from either side. The attack can happen from the front and the back, because this is a planar carbocation. So the attack can happen from either side. And once the attack happens, then what will you form at the end, people? Then at the end you will form two isomers. Yeah, one of them will look pretty similar to this one. Yeah, you must be wondering, okay, how is this OH now? We had attacked OH2. Don't worry, if this was OH2, you just remove an H positive from here. Where will you take that H positive? Give it to the Br. It will become HBr. Fine. So an H positive can be removed to turn the OH2 into an OH group. And the other structure that will be formed will be the mirror image of this one. And over here, coming towards you is this. Cool. Can you see both of these are non-superimposable mirror images of each other? What do we call these? These will be called enantiomers. And a 1:1 mixture of enantiomers is known as a racemic mixture. So in an SN1 reaction, you take a polar protic solvent, you preferably take a bigger substrate that does not want to undergo SN2 reactions. You take a weak nucleophile so that the nucleophile itself doesn't want to do an SN2 reaction. And then finally what you get is a 1:1 racemic mixture. Very nice. SN1 reactions are entirely revised now. So my dear friends, do you realize that this is a two-step reaction? SN1 reaction is essentially a two-step reaction. It's not a one-step reaction anymore. And now in these two steps, can you tell me which is the slower step? The first step is formation of the carbocation. The second step is formation of the final product. So my dear friends, the first step is creating an unstable species. Carbocation is a charged species. It is an unstable species. That's why we call it a reactive intermediate. So the first step over here is the slower step of the reaction. Yeah, this is the slower step out of the two, and therefore we will call it the rate determining step. RDS means rate determining step. Cool. And practically speaking, this is actually a reversible reaction. So the first step is the rate determining step. The second step is the formation of the final product. So if you can form stabler carbocations, this step will happen faster. If you cannot form stable carbocations over here, this step will be even slower. So species that can form better carbocations give better rates for SN1 reactions. Alright. Now my dear friends, let's just make the energetics diagram over here directly. This is a two-step reaction, yes. It's a two-step reaction. So do you realize you will have two peaks over here? this reaction will look something like this perhaps. This is your reactant, this is your product, and this in the middle, this is what? This is where your intermediate is formed, which is a carbocation in this particular case. Reactive intermediate is formed over here. So first step and then second step. Very nice. SN1 reactions entirely revised on this one page. If you want to take a screenshot of this, please do so. And I have my handwritten notes, very nicely written for revision. So in case you guys want this, I can share this with you on Telegram later. Badhiya. Very nice, people. So let me see if I have some points written down. There you go. It's a two-step reaction, formation and rearrangement of carbocation and attack of nucleophile. Rearrangement of carbocation we'll do when we solve questions on Wednesday. Okay. So how do we do rearrangement of carbocations? We'll practice that while solving questions on Wednesday. If you want to, study it from the scratch, how does carbocation rearrangement take place? Then you should check out the full class links in the description box down below. Okay. Chalo badhiya. Rate does not depend on the nucleophile. The nucleophile is weak, right? It does not want to react. Rate determining step only involves one molecule that's just breaking apart. So the rate the rate is determined only by the substrate, the alkyl halide that we've started with. Order is one, molecularity is also one, because one molecule is breaking apart on its own. Nothing is forcing it to break apart. So unimolecular reaction. Product is a racemic mixture. Very nice. Siva, Raja, you are absolutely correct, man. If you are making notes on your own, that's the best thing. This is just for, I don't know. In case anyone wants. Cool. All right. So, can you tell me what's the correct option over here? We're talking about the rate for the SN1 reaction. Rate for SN1 reaction, which one is the correct option? Tell me. Maintaining such a heavy mustache is also difficult. You have to keep it in shape constantly, otherwise it will just drop down. That's why I keep doing this all the time. Tell me, what's the correct answer? See, for carbocations, 3 degree is very good. Yeah, 3 degree carbocation is more stable than 2 degrees, more stable than 1 degree, is more stable than a methyl carbocation. I'm sure you remember this from general organic chemistry times. Yeah. So people, this one over here, this is a 2 degree substrate. This one over here, this is a benzilic substrate. What about this guy? This is just a 1 degree substrate. Now, in the case of a benzilic species, when you remove the chlorine, you will have a carbocation that is resonance stabilized because of the benzene ring. So this will give you the best rate even for SN1 reaction. So keep it in your mind that alilic species and benzilic species are great substrates for SN1 reactions as well. Yeah. So over here, the best rate will be for 2, then the next will be 1, and then the worst will be 3. So I think option number B is the correct answer. ठीक है जी, बढ़िया. So when we are talking about carbocation stability, resonance is always better than some hyperconjugation, than just 1 degree carbocations. All right. Now I hope you won't make a mistake again. Sivaraja had given the correct answer. Very nice. Chalo, good job. Now people, let's move on to the next reaction. SN2 and SN1 are done. So now the next reaction that we'll talk about is the E2 reaction. E stands for elimination. And 2 obviously stands for bimolecular. So in E2 reactions, what happens is something that's similar to SN2 reactions. Okay, so E2 is, let's say, SN2's cousin. Okay, SN2 and E2 reactions always compete with each other. Fine. So what happens in an E2 reaction? Okay, let me just make a nice substrate for you. Just give me one moment. So what we have in an elimination reaction such as this, let me take a species where you have a leaving group like this. This is a carbon, this is also a carbon, and on this particular carbon you have hydrogens. Yeah, so let me just draw this in such a manner first. Hydrogen, 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 hydrogen. Okay, so what's going to happen over here, that bromine is as usual your leaving group, and one of the hydrogens from this carbon is going to be removed. Okay, so if this is the bromine and next to bromine is your alpha carbon, then next to it is your beta carbon. Alpha, beta, and the hydrogen on the beta carbon is being removed. So such reactions are also known as beta elimination reactions. Fine. Such reactions are also known as beta elimination reactions. So this entire substrate that we've made, I'm going to make it in a better manner. I'm going to make it like this. Get it? I'm just showing you one hydrogen. Other hydrogens will not be shown obviously because this is just a bond line formula, right? So in bond line formula, we don't need to necessarily show the hydrogens. I'll just show one of them which is useful for us. Okay? Badhiya. Now in E2 reactions, what we use is a strong base. We need a strong base over here. Again, what can we use as a strong base? OH negative. Okay? So let's again use OH negative as our strong base. So what happens in an E2 reaction is that OH negative wants to capture this proton. This proton has these 2 electrons that it will leave with the carbon. So this pair of electrons moves to the carbon over here. Fine. At the same time, this pair of electrons, a bond is a pair of electrons, right? This pair of electrons moves towards bromine. All of these things happen at the same time. So OH is capturing the proton. This particular bond is being broken towards carbon. This is getting a negative character, yes? I'll write negative character. This bond is being broken towards bromine. So bromine is taking away the electrons because obviously this is more electronegative than the carbon over here. So carbon gets a partial positive character. All of this is happening simultaneously in a single step. And once this happens, what will be the final product? The final product will be a double bonded system. Negative and positive combine together to make a double bond. Of course, you have your water molecule that gets formed at the top and a Br negative that leaves away from the side. So this E2 reaction is once again a single step reaction. Single step reactions, there's a better word. Instead of calling it single step reaction, we also call this a concerted reaction mechanism. Concerted means single step. See, what happens in a concert is that every musician is in sync with each other. they're all very well synchronized with each other. So over here, all the steps are very well synchronized with each other. So it's like a concert. That's how you can remember this idea. Concerted double bond. See, why does a beta elimination happen? Because after beta elimination, you can have a bond that gets formed. In an alpha elimination on the same carbon, how can you form a bond? Yeah, you are taking away this and you are taking away the hydrogen as well. So alpha eliminations are not very common. Alpha eliminations happen in the case of formation of a specific intermediate called dichlorocarbene. So when we do the carbylamine test, we'll talk about dichlorocarbene in amines chapter. So that is where an alpha elimination happens. But yeah, so we have the formation of an alkene over here. Very nice. Now there is one very important idea about E2 reaction mechanisms that most students ignore, and that is where they lose their marks. So the important point over here is anti-periplanar geometry. This is extremely important, people. For E2 reactions to happen, we need anti-periplanar geometry. What does that mean? Let me try to show that to you using a model once again. Okay, I'm going to zoom in so that you can see the model better. Fine, this is the model that we have. Now this yellow thing, okay, is, let's say, the leaving group. Okay, wait a second, this model is sort of incorrect. Just give me one moment. Yeah, now this is fine. Cool. So this yellow thing is your leaving group. This is the bromine that wants to leave. Now, my dear friends, this bromine has an electric field over here. Yeah, this entire region has bromine's electric field. So the base that has to approach, the strong base, cannot approach from this side. Yeah, the strong base cannot approach from this side. So the strong base has to approach from the opposite end. Yeah, the strong base has to approach from the opposite end. And my dear friends, what is observed is that the strong base prefers to do the reaction in this particular geometry. This is the leaving group over here. The hydrogen that wants to leave with the base has to be opposite to this particular bromine. Yeah, this is the leaving group that leaves. This is the hydrogen. Can you see they are basically in the same plane? This is the hydrogen that wants to leave. This is the bromine that is leaving. Can you see they're essentially in the same plane? Yeah. Can you see bromine at the top, hydrogen at the bottom? They're essentially in the same plane, but they are absolutely opposite to each other. Yeah. This one and this guy, they are absolutely opposite to each other, but in the same plane. This is known as anti-periplanar geometry. This allows for the best orbital overlaps between the base, this particular hydrogen, then the double bond getting formed, and this bromine leaving. This is what happens then. This guy leaves from the bottom, this guy leaves from the top side. Anti-periplanar geometry. Okay. So if you try to do this elimination, let's say from here and here, no, this is not going to happen. Yeah, the elimination will happen in an anti-periplanar fashion only, E2 elimination. So bromine leaves in this direction, the proton leaves in exactly the opposite direction, but in the same plane as such. Cool. So this is what we mean by anti-periplanar geometry. And the application of this anti-periplanar geometry comes when we talk about cyclohexane based substrates, which I'll show you in a while. Yeah. So let me take an example for you. Yeah, this is a good example. So let's take a cyclohexane, something like this. So my dear friends, in cyclohexane, you know about equatorial and axial bonds. Yeah. Let me just show you equatorial and axial, then I'll show you about the anti-periplanar thing over here. So in cyclohexane, on every carbon there is one axial bond. I'll make all the axial bonds right now. Yeah, these are all the axial positions, and then there are equatorial positions. Equatorial, 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 and equatorial. So the blue ones are equatorial. Okay, and the green ones that we've made are axial. Now, can you see that this axial and the axial next to it, they are anti-periplanar? This axial and this axial anti-periplanar, this axial anti-periplanar. All the axial bonds are already anti-periplanar to each other. Very nice, right? But if you notice these equatorial bonds, they are not able to form anti-periplanar. Yeah. Axial is this and this. Very nice, anti-periplanar. Equatorial bonds are like this. Nah, this is not anti-periplanar, right? This is something weird. So, whenever you want to do elimination in cyclohexane, it is imperative, it is absolutely necessary that your alkyl halide that's leaving, your leaving group, and the hydrogen that is getting removed, both of them have to be in axial positions. They have to be in axial positions. Let me draw the examples for you. So let's say there is a case where you have a bromine over here and a hydrogen over here. E2 reaction will happen. Perfect. E2 reaction can happen over here. How will it happen? Your OH negative can approach from this particular side. This bond can break. This bond can break. Hydrogen leaves in this direction. Bromine leaves in this direction. Anti-periplanar. Very nice. Yeah. Cool. So you have to keep your leaving group and your proton in axial positions on adjacent carbons. Fine. So let me ask you a couple of questions with this concept in mind. Okay, now I'm going to ask you some questions with this concept in mind, and this is one of my favorite parts to ask about. So we have something like this. Okay, this will not only revise confirmers for you, this will also make this class even more entertaining for us. So let's say we have a chlorine over here. Okay, and we have a CH3 that's going behind the plane. What you do is you do an E2 reaction over here. So what is required for E2 reactions? You take a strong nucleophile. Yeah, let's say you take NaOH over here. Strong base, sorry. Yeah, there's a strong base. Now to boost elimination reactions, what you can do is you can provide the reaction some heat. Okay, whenever heat is given, elimination is favored. When heat is not given, substitution is favored. So keep this in your mind. When elimination is favored, heat will be given. When substitution is favored, heat will not be given. So that's a very good hint to understanding whether E2 will happen or SN2 will happen. So over here heat is given, strong base is given. So over here E2 reaction is going to be favored. Now my question to you is, what will be the product? Will you get this as the product? Let's call this A. Or will you get this as the product? I will call it B. You have to tell me which product will get formed. And the application of what I just told you, axial equatorial, will be useful over here. So in order to solve this question, make the cyclohexane chair form, put axial equatorial everywhere, then I've already told you, for elimination to happen, this chlorine, this leaving group, has to be in the axial position. So if this has to be in axial, where will this be? Then think about it. Yeah, I'm giving you a moment, think, and then I will also solve it for you. Enjoying the class? I'm sure you are. So, this is what our chair conformer of the cyclohexane will look like. And for the elimination to happen, this is the, let's number the carbons, okay? 1, 2, 3, 4, 5 and 6, let's say. So this is 1, this is 2, this is 3, this is 4, this is 5 and this is 6. Cool. Now on this particular carbon, the chlorine has to be at the axial position. Perfect. Chlorine has to be at the axial position. Now if the chlorine is at the axial position, my dear friends, you have to judge, okay? What you have to judge is on the carbon number 6, this is the axial bond and this is the equatorial bond. Carbon number 6 has a CH3 on it. Out of axial and equatorial, where will the CH3 be? Where will you have that CH3 on the carbon number 6? Will it be on the axial position or the equatorial position? See, in this structure it is given to you that chlorine is pointing towards you, CH3 is pointing away from you. Basically this is a trans configuration. Chlorine and CH3 are in the opposite directions. In this diagram, do you realize that this chlorine is pointing downwards? This chlorine is pointing downwards. So the CH3 has to be pointing upwards in this diagram. This diagram clearly shows you chlorine and CH3 are in the opposite direction. How do we interpret it in this diagram? If chlorine is pointing downwards, CH3 has to be pointing upwards. Which bond out of these two is pointing upwards? Axial bond. Yeah, this is pointing upwards. Equatorial bond, technically speaking, is pointing towards the bottom, right? This is pointing downwards. So you can't have chlorine and CH3 both pointing downwards. No, the structure says it has to point in the opposite direction. So chlorine is pointing downwards, the CH3 will be pointing upwards. So therefore, because of the structure that's given to us, chlorine, CH3. So where does the hydrogen go? Hydrogen goes here. And now do you realize that this hydrogen cannot be eliminated? You have to keep chlorine in the axial position. CH3 is in the axial position because of the structure that we've been given. This particular hydrogen cannot be eliminated. Yeah, no anti-periplanar geometry is possible over here. So the only hydrogen that can be removed is the one that will be on carbon number 2. This one. Nice. Yeah. So the only hydrogen that can be removed is this one. This guy can be eliminated. So therefore, double bond will not get formed towards CH3. It will get formed away from CH3, which is option B over here. So even though looking at these two structures, you might think that this is a stabler double bond. Yeah, this double bond has more alpha hydrogens. This double bond has less alpha hydrogens. So this being a more substituted double bond, you might be tricked into thinking that this is the answer, but no. This cannot be formed because of the reaction mechanism that we are taking. Nice. Hartanam, that's good, man. That means you're understanding things. Yeah, boy. Buddy, what I can suggest you to do is revise while practicing more questions. Okay. And if you want to watch regular classes of mine, the links are in the description box down below. Anyway. Sivaraja, yes, that's where you might make a mistake. That's why this is a good question. Cool. Acha. Do you want me to ask one more question similar to this? Black caps because this is not anti-periplanar to the chlorine. Okay. So one more question that's very similar actually. Okay. Let's do this. There's a bromine over here. There's a CH3 on this particular carbon. There's a CH3 on this carbon as well. And you're trying to do an E2 reaction. Use whatever suitable reagents you have to use. What's the product that will get formed? Or let me ask you, will there be a product? This is a very nice question that can come in your examination, okay? They'll give you options. They'll give option A being something like this. You know? They'll eliminate from here. They'll give you maybe option B, something like this. Okay, let's say you take NaOH and you take heat. Or instead of NaOH, you take a base that cannot act as a nucleophile. Alright, let's say you take, what is this tert butyl? Okay, let me tell you. So basically, if you have something like this, carbon, CH3, 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 and then you have O negative, K positive. So this is a tert butyl OK. This particular species is a good base, but it is a very bad nucleophile. Why is it a bad nucleophile? Because it has steric hindrance in its own structure. So because of its own steric hindrance, it can't act as a nucleophile, it can only act as a base. So in this particular question, a very strong base has been given, heat has been given, so you understand that okay, E2 elimination is possible. That is an option that might be given to you. This is an option that might be given to you, let's say something like this. Maybe, I don't know, they give you this as an option. Option C is none of the above. So in this particular question, you would have to choose none of the above because there is no anti-periplanar hydrogen possible here. Yeah. Bromine, if you keep bromine axial, then this CH3 will be axial on one side, this CH3 will be axial on the other side. So there's no hydrogen that's anti-periplanar in this structure. Therefore, no product is possible. None of the above will be the correct answer then. Nice. So let's do one more question and we'll have to worry about the stereochemistry over here. Okay, we'll have to worry about the stereochemistry over here. So let me just make that structure for you. And if you can do this, then a lot of questions of alkyl halide chapter will become easy for you. So let's say we have something like this. Hydrogen, hydrogen, CH3 and CH3. And then we have a bromine over here. And what we do is we put alcoholic KOH. So whenever you see alcoholic KOH in your reactions, okay, keep this in your mind. Whenever you see alcoholic KOH in your reactions, this implies that you have to do an E2 reaction. Simple as that. Now, you have to form the product with the correct stereochemistry. The right stereochemistry is very important over here. Elimination hai, E2 hai, badhiya hai. But what will be the product with the stereochemistry? So people, tell me, first of all, try to convert this Fisher projection into a Sawhorse projection. I've taught you that exercise on Tuesday. How to convert a Fisher into a Sawhorse projection. Yeah, let me do that for you. This is what we can do. This is the blue carbon, let's say this one. All right. So at the bottom I can write the C6H5. Coming towards you, I can write the hydrogen, and sort of going away from you, I can write the CH3. Over here also, what I can do is at the bottom I will write the bromine. Going away from you, I can write the CH3, and coming towards me, I can write the hydrogen. This is one Sawhorse projection that we've made. Now try to convert this Sawhorse projection into something where this bromine and that hydrogen are anti-periplanar to each other. Yes, can we do that? So basically, this bromine has to be at the bottom and this hydrogen has to be over here. So if we rotate it something like this, just slightly rotate it, yeah? Hydrogen at the top. So on the right hand side, we have our C6H5. On the left hand side, yeah, we have our CH3. What about the front carbon? Again, on the right hand side top, we have our hydrogen. On the left hand side, we have the CH3. And now from this particular Sawhorse projection, you will do the elimination. Bromine will leave, hydrogen will leave. Let's say the OH negative approaches from here, cool. And then a double bond will get formed in this particular position. So when the double bond gets formed, the positions of this benzene ring, the CH3, the CH3, very important. Yeah. So after the double bond gets formed, at the back carbon, you have your C6H5 towards the right hand side, towards the left hand side you have your CH3, and on this particular carbon, on the right hand side you have the hydrogen, on the left hand side you have the CH3. This is the product that will be formed. Now can you tell me whether this is E or Z? Is this Entgegen or Zusammen? What is this? Quick, I'm looking for your answers in the chat box. Saravana, very nice. Haritanam, very good. Sivaraja, Areva. Vaishnavi, chalo, for Vaishnavi I'll have to show you what the correct answer is. So what we do to decide E and Z is we divide it into two halves. On this side, which one has the higher priority, CH3 or benzene? Obviously benzene, because there are more carbons over there. Yeah, so this gets higher priority. I'll just put a tick mark over here. On the other side, out of CH3 and hydrogen, which one has the higher priority? CH3 has the higher priority because carbon has a higher atomic number than hydrogen. So now, across the double bond, can you see the high priority groups are on the opposite sides? Yes. Since the high priority groups are on the opposite sides, this has, what will we call it? We'll call it the E isomer. E stands for Entgegen, which is a German word for opposite. EZ isomers is a part of geometrical isomerism. Geometrical isomerism में अपन करते हैं ना cis and trans. EZ is a brother of that. All right. So E stands for Entgegen, which is a German word for opposite. How you can remember it is opposite. You can call it opposite to remember it. Z stands for Zusammen, but you can call it Zame. Opposite Zame, EZ. In case you guys want to learn about isomerism properly from me, all you need to do is search on YouTube for Epic GOC, and Epic GOC you have lectures. You can go to the geometrical isomerism class directly if you've covered all the others, and then learn about Entgegen, Zusammen, CIP rules, etc, etc. Fine. Pretty cool. Nice one, right? So this is where the fun of organic chemistry lies. And the more questions you do, the more fun such as this you will be able to have. Chalo. So some points about the E2 reactions. Yeah, let's do this. It's a one-step reaction, concerted. Rate is exactly the same as SN2. So looking at the rate of the reaction, you can't decide whether the reaction is an SN2 or E2. In the laboratory, it's very difficult to actually see whether the reaction happening is an SN2 reaction or E2 reaction. Why? Because in the laboratory, you will just get a muddy solution at the end as your product. You will not be able to see its structure, yeah? So you'll have to do further experiments to figure out whether you've had substitution or elimination, whether you form an alkene or a substituted alkene. So rate is the same, order is 2, molecularity is 2, exactly the same as your SN2 reactions. Base attacks from the backside, very similar to SN2. Strength of the base increases, rate of the reaction increases. Similar to SN2. This is where this reaction differs from SN2 reactions. In SN2, steric hindrance stops the reaction from happening. But over here, if you have a more substituted substrate to start with, you form a more substituted alkene at the end. Yeah, if you have a more substituted substrate at the starting, at the end the alkene formed is more substituted. Now because of more substitutions, alkenes become more stable because of hyperconjugation, yeah. More substituted alkenes are more stable because of hyperconjugation. So over here, this is where this is different from the SN2 reactions. 3 degrees more reactive than 2 degree is more reactive than 1 degree. And therefore, if you have a choice to form 2 different alkenes, then you will choose to form the more stable alkene. ZF product is formed. If you have a choice. For example, if this is the case and you try to do an E2 elimination on this, I'm sure you can realize we can eliminate on this side as well, and we can eliminate on this side. The major product will be the more substituted alkene. This will be the minor product. Okay. So major product, why? Because this has more alpha hydrogens. The alkene has more alpha hydrogens, more hyperconjugation, better stability for the alkene. Cool. And finally, we've seen no intermediate is formed, only a transition state is formed which has alkene-like character. Okay. Just a transition state is formed. If you want to draw the transition state, I'm going to draw it for you over here. So this is where your Br is leaving. This is where your hydrogen is leaving. This is your OH negative. Yeah. And at the same time, we realize that the carbon over here is getting partial negative character. This is getting partial positive character. So there will be bond formation starting between these two. So this is a double bond character. This is the transition state, and the transition state has an alkene-like character. So therefore, more substitution, or if you have resonance, that will stabilize the double bond, will stabilize this transition state as well. Very nice. Badhiya ji. E2 reactions are also done. Now it's time for us to do E1 reactions. Oh damn, it's already almost an hour and a half. Let's see how much we can do in these 2 hours. And I'm sure a lot of things will still remain, we'll continue. Okay, in the next week I might take an extra class for you. At night you guys are free, right? Black caps, I'm glad to hear that time flew by so fast. But next week, if I want to take an extra session for you, then what day can I take, people? Because your classes are at 6 p.m. and 9 p.m., right? So on Wednesday, you already have a class with me at 10. I can't take a class at 9 p.m. because I already have to take a class at Vedantu JEE Hindi channel. So Johan, I have to take a class at 8 p.m. on the other Vedantu JEE channel. Yeah. No worries. I'll figure out a time for you guys, most probably some slot at night, and we'll do it. Okay, I'll talk to one of the other teachers. I'll talk to Nomita ma'am or Shreya sir or Namrata ma'am and see if they are finishing one of their classes a little earlier, let's say 9:30, 10. Even at 10:30, if they're finishing, I can do a class with you. Cool. So we'll figure that out. So let's try to do as much as we can in the next, say, 30 minutes, and then yeah, we'll keep pushing it. It's okay. But yeah, chalo. So E2 reactions are revised, people. Now the next reaction that we're going to talk about is going to be your E1 reactions. Yes. Elimination, unimolecular. So this one is your SN1 reaction's cousin. And the first step for E1 reaction and SN1 reaction is entirely the same. The first step for E1 reactions and SN1 reactions is entirely the same. You basically have the formation of a carbocation. So if you have a substrate like this, and if you simply give it a little bit of heat in once again a polar protic solvent, what's going to happen is the bromine can leave and you will have a carbocation formed. Same step as the SN1 reaction. Now the next thing that we can do over here is provide it with a relatively weak base. Like we did in SN1 reactions. We use a weak nucleophile over there, we'll use a weak base over there, over here. Yeah. So if we use a weak base, then what can happen is, this is a proton, the base can capture the proton can leave away, and finally you will get your alkene. Simple. No rocket science over here. Carbocation. And over here, do you realize that the trans alkene will be formed and the cis alkene will also be formed? In the previous case, in E2 reaction, we had to look at the source projection, make the anti-periplanar geometry, very carefully take away the bromine and hydrogen, and then figure out what's the final product. Over here, you don't need to worry about that jazz. Over here, the carbocation that we form is planar. So the elimination can happen in either direction essentially. Both of these products are possible. Cool. Generally speaking, trans is slightly more, slightly major compared to cis products because this is a little more symmetrical in nature. There is zero dipole moment over here. Stacking is very nice. You can stack a lot of trans structures next to each other. So generally because of these ideas, trans is better. In cis, you have dipole moment and then you have some steric hindrance over here as well. So this is a CH3. This is also a CH3. So there are these interactions which make cis slightly more unstable compared to a trans structure. So generally you see trans structures are formed in major quantities. Cis structures are also formed in slightly lesser quantities. So once again, the energetics of this reaction will also be something like this, similar to your SN1 reaction. Even the rate law will be very similar to SN1 reaction too. So actually, to judge whether SN1 is happening or E1 is happening is very difficult. You judge that by the nature of the base essentially. There's no other option. Okay, so when we do questions, then we'll realize whether to do SN1 or whether to do E1. Again, heat is a deciding factor. If you provide heat, then elimination reactions are more favored. Cool. बढ़िया. So E1 के भी थोड़े points लिखे होंगे मैंने. These are the points for E1 reaction. Two-step formation of carbocation, loss of proton to form pi bond, Rate law is exactly the same as the SN1 reaction, so is the order and molecularity. The reactivity again is the same because you're forming a carbocation, so 3 degrees more stable than 2 degree, more stable than 1 degree. Nice. ZSF product is formed. ZSF product means more substituted alkene is favored. Good leaving group increases the rate of the reaction. Obviously, similar to SN1 unimolecular reaction, right? So if the leaving group is better, if the leaving group easily can leave, then your carbocation will be formed faster. Polar solvent increase the rate of the reaction. Addition of silver salts can catalyze the reaction. So pretty much similar to your SN1 reactions. Johan, today I'm taking sort of a strategy session on the other channel, and then from next week onwards I'll be doing organic chemistry everywhere. Badhiya. So people, E1 reaction is also done. Now comes the most interesting reaction mechanism out of all of these. All of these were also interesting, but now the one that we're going to talk about is even more interesting. E1CB. What does this E1CB mean? This essentially means that this is a unimolecular elimination. Unimolecular elimination via conjugate base. Unimolecular elimination via a conjugate base. Interesting. Yeah. Now, E1CB reactions are kind of peculiar. Okay. They are a little strange. So, you need very specific conditions for E1CB reactions to happen. Let me tell you what those reaction conditions are. The leaving group that you need has to be a poor leaving group. It has to be a bad leaving group. A very common example of a bad leaving group would be fluorine. Okay. So, fluorine is a poor leaving group. This just does not want to leave. Why doesn't it want to leave? You'll be like, sir, F negative is a good species. We've seen F negative here and there. The thing is that F negative is very small. It's extremely tiny. It has high charge density. It's a reactive species. Does not want to get formed. It's so reactive in nature. So you have to provide a lot of energy for fluorine to leave. It's easy for iodine to exist as I negative because this has very low charge density. Yeah, the outermost electron is far away from the nucleus of iodine. So it's just chilling out there. But fluorine, very close to the nucleus. This electron is repelling all the other electrons that are very close to it in the second shell itself. Yeah. So fluorine has high charge density, very reactive species, iodine chill. So that's why if you have fluorine in alkyl halides, it's very difficult to do reactions with fluorine, okay? Extremely difficult to do reactions with fluorine. So now this is a very poor leaving group. What you can do in such cases, okay? What you can do in such cases is put a strong base. Alright, you put a decently strong base over here. Now the strong base will approach this structure and see that, okay, I have this hydrogen and this hydrogen available to me. I can abstract either this hydrogen or this hydrogen. So the strong base will try to abstract the hydrogen. It will take the hydrogen away. Over here, the first step is to take the hydrogen away. Now, my question to you is, which of these hydrogens will be removed? There are two options that you can form. This is one of the options, and the other option is this one. Yes, these are the two options. Either you remove the more substituted hydrogen or you remove the less substituted hydrogen, 2 degree versus 1 degree. So, once the base has acted on either of these protons, you form either a 2 degree carbanion or a 1 degree carbanion. So this is what, 2-degree carbon ion, and this is a 1-degree carbon ion. Which one is formed, people? What do you think? Which one out of these should I prefer? And now we're talking about carbon ions. Carbon ions, their stabilities are opposite to that of carbocations, right? In carbocations, inductive effect and hyperconjugation will help them get stable. Over here, carbon ions want to be the least substituted, because in the first carbon ion, there is inductive effect from this side, plus I effect, that will destabilize it even further. Carbon ions are better when they are not substituted, when they are alone. There is no inductive effect to bother it. There is no plus I over here to bother it. So my dear friends, this is a better carbon ion. This one over here will not get formed. And now do you see the reaction is already very entertaining. Till now we've been making more stable, more substituted products, right? Because carbocations were involved, alkene-like transition states were involved. All of a sudden, we are making less substituted products. So the first step in E1CB is the action of a base. And the second step in an E1CB reaction is the loss of leaving group. And then finally what will happen? A less substituted alkene is formed. This is not a Sage-Zeff product. This type of an alkene, which is less substituted, this is known as a Hofmann alkene. Yeah. Haritanam, yeah, okay, just forget about it. So a less substituted alkene is formed, which is known as a Hofmann alkene. Beautiful, right? So in this particular procedure, the important thing is you have to have a poor leaving group. Okay? And you need a strong base, and generally, bulky bases give you better E1CB products. So I'll write that over here as well. You need a bulky base. Bulky base means the base itself has a lot of steric hindrance. So if the base itself has a lot of steric hindrance, it will not be able to go inside the structure. It will just stay outside the structure and remove the outermost proton very easily. So bulky bases will help the E1CB even more. One example of a bulky base we already saw, tert-butyl O negative. Very nice. So my dear friends, this is step 1 of the reaction and this is step 2 of the reaction. Can you guys tell me which one is the rate determining step over here? Black caps, I'm glad you enjoyed. Can you tell me which one is the rate determining step out of these two? This is where things get even more interesting. I want to see that in the chat box. Sivaraja is saying that the second step is the rate determining step. Sivaraja is saying that second step is the slower step. Okay. Anyone agrees with him? The black caps agrees with him. So does Sai Trisha Reddy. So does Arvindan. Very nice. So people, the thing is that the first step is just an acid-base reaction. The first step is just an acid-base reaction. So out of these two, this is slightly faster. Okay. Out of these two steps, the first step is slightly faster, not very fast by the way, okay? Because you're still forming an unstable intermediate. You're still forming a carbon ion. You are still, removing a proton from an sp3 carbon, which is very difficult to do. So this is slightly faster because technically speaking it is an acid-base reaction. Okay. And the second step in this particular case, which is the loss of the leaving group, is compared to the first one, slightly slower. So in reality, there is not a lot of difference in speed between these two steps. This is just slightly faster, this is just slightly slower. And that's one more beautiful thing about the E1CB reactions. Cool. So you form Hoffman products over here. Very nice. Now people, quickly, let's talk about the rate law. And the rate law over here is also interesting. Since I said both steps have similar speeds, not too different. Therefore, actually the rate depends both on the substrate that we have and the base. Okay, both concentrations. So if you increase the amount of base, the rate will increase. If you increase the amount of the substrate, the rate will increase. So even this step contributes to the final rate law. Interesting. Yeah. So essentially your order is 2. But again, if you think about the slowest step of the reaction, the number of molecules in the slowest step are just 1. This is just 1 molecule, right? So the molecularity of the reaction is still equal to 1. Molecularity is equal to 1. So order is 2 because power is 1 plus 1. Molecularity is 1 because in the slowest step there is just 1 molecule that's acting. Nice. Darun Karthik is asking, can I clear JEE if I start preparing from now? See, you can definitely crack it. You should aim for the longer goal, that is the second attempt of JEE. The first attempt, you should take it as a practice attempt, but still you should practice a lot of questions till the first attempt also. Don't skip the first attempt. But the perspective that you have to keep in your mind is you are running for the longer game, which is the second attempt. Okay? Possible hai. Sab possible hai mere dost. Cool. Badhiya yaar, today's class is actually really fun. Alright, so this is all about E1CB reactions. Now, one thing that I want to tell you that I don't think anyone else will. Okay. Now the next segment is a little special for all of you. And we'll talk about the elimination spectrum. See, E1 reaction, E1CB reaction, E2 reaction. The things that we've done with these reactions are all on paper, right? In reality, do you realize that if an elimination reaction is happening, it's possible for it to happen via E1 reaction and via E2 reaction? Let's say majority of the reaction happens via E2 mechanism. There will be a slight minority of the reaction that undergoes a carbocation reaction mechanism, right? That's always possible inside a reaction mixture. There are so many molecules, moles of molecules, right? 1 mole is a huge number. So there are moles of molecules that you're dealing with. And some of those molecules will have the energy to form a carbocation, even when the conditions are not that conducive for carbocations. So what happens in reality is that no reaction is perfect. No reaction is a perfect SN1 reaction. No reaction is a perfect SN2 reaction. All of these SN1, SN2, E1, E2, E1CB, all of these are competing with each other. And most of the times, all of them will happen. One of them will be a major product. Others will be formed as minor products. So in reality, things are not as transparent as we've made them out to be. One idea that I'm going to discuss now is known as the elimination spectrum. So on one end of the spectrum is your E1 reaction mechanism. Yeah. A1 reaction mechanism, we say that it is in two distinct steps. The first step is leaving group leaves, and the second step is essentially your H positive taken away. Yeah. On the other end of the spectrum, we have the E1CB reaction. Complete opposite, right? The first step is your H positive gets taken away, and the second step is that your leaving group leaves. In the laboratory, in reality, the reactions happen somewhere in the middle of this spectrum. Bang in the middle, what do you have? E2 reaction. Both the steps happening simultaneously. Yeah. So theoretically, if you have E2 reaction, both steps will happen immediately at the same time. If you have theoretical E1CB, first H positive is taken away, then leaving group leaves. If you have E1, first leaving group leaves entirely, then H positive is taken away. But in reality, the reactions will lie somewhere in the middle. Let's say there's a reaction that lies somewhere here in the spectrum. What does this mean? This means that the reaction starts with H positive being taken away. Now, while the H positive is being taken away, the leaving group realizes why I also have to leave. So H positive is already, let's say, 50% gone. The bond is 50% broken already. Then the leaving group also starts to take off. So both the steps are not happening exactly at the same time. It's not that one step is happening first, then the next step is happening. The first step starts, and then in the meanwhile, the second step also starts. That's how a real reaction would look like. A real reaction somewhere here means that the leaving group leaves, leaving group starts to leave, and then the H positive also realizes, okay, I also have to be taken away by a base. That's what real reactions are. So, there's a set of data that I will share with you, which will make it even more clear for all of you how the reality is. So what we are doing is, we're doing this sort of a reaction. Okay. I think this is the last thing that we'll be able to discuss in today's class, but okay. So this is your leaving group, all right? And this is a hydrogen that can leave, this is also a hydrogen that can leave. If you form a double bond in this direction, Sadzev product, this one will be a Hofmann product, yeah? So you do whatever reaction you do. The base that we take over here is ethoxide ion, ethanol's ion, fine. So if you do this reaction with ethoxide ion, the two possibilities that we have are either a Hofmann product or we have a Sadzev product, yeah? Now, depending on the leaving groups that we take, okay, depending on the leaving groups that we take, if we take, bromine as the leaving group, this is the Zaitsev product, this is the Hofmann product. If bromine is the leaving group, 81% of the product is Zaitsev, 19% of the product is Hofmann. See, nothing is perfect in nature, yeah? Most of the product is Zaitsev, but some of the product is still Hofmann. So can you think, where does this lie on the spectrum? Mostly Zaitsev, but a little Hofmann. So this reaction, if I have bromine as the leaving group, will lie somewhere here on the spectrum, let's say. 80% towards E1, just 20% towards E1CB. Yeah. If I have chlorine as the leaving group, 67% is Sadzev product, and the remaining 33% is your Hofmann product. If you take fluorine as the leaving group, then the percentages change drastically. Hofmann product becomes the major product. 70% Hofmann. If you have even worse leaving groups now, Okay. Silicon with 2CH3, something like this. If this entire thing is your leaving group, okay, then 26% ZSEV and the remaining 74% Hoffman. And then if you have an even worse leaving group, three degree amine, if that is your leaving group, just a second. Yeah. Then you have only 5% ZSEV product and 95% Hoffman product. Haritaram, because bromine is a better leaving group, so it starts to leave first and then the H positive gets taken away. So the reaction is closer to E1 in this particular case, and the reaction is much closer to E1CB in this particular case. The entire spectrum. Nice, right? Badhiya. You've discussed a good number of things today, although I would have liked to discuss more things with you, but apparently we don't have the time to do so. Yes, black caps, absolutely. Tarun, so the thing is with organic chemistry, it's always better if you have a teacher to guide you, because organic chemistry is a bit too vast. You can try doing it from the book and then going to the previous year questions, but you will somehow or the other need the guidance of a teacher for sure. So you can check out the links in the description box for my regular classes, for my longer classes. If you want to learn general organic chemistry from me, you can search for this series on YouTube called Epic GOC, and this will also help you quite a lot. Yeah. Black caps, yo. I'm glad you're enjoying the class. Haritanam, my throat is okay, not perfectly fine. But anyway, people, I think this is the extent of what we can cover in today's class. So good, we've covered SN1, SN2, E1, E2, E1, CB, and I'm sure you learned a lot of new things from me and you were able to revise all the concepts of these reaction mechanisms from me. So in the next week, we already have a session planned on Wednesday for the previous year questions of reaction mechanisms and alkyl halides. I will also definitely cram in a theory session for revising alkyl halides chapter. So probably a 2.5 hour session. I'll discuss with the other teachers and see where we can put that in the schedule. It'll be at night, not in the daytime. So at night sometime, let's say maybe 10:30, Monday or Tuesday, we'll do a revision session for alkyl halides as well. Cool. Badhiya. Johan, we're already at the weekend, so Monday or Tuesday we'll try to do that. Haritanam, we'll do a beatbox session some other time, man. It's okay. Something that'll keep you coming to the classes. But anyway. So people, what I would appreciate from you guys is if you share this session with some friend of yours, if you feel like, because it'll be good for us to have a little more reach. Because when we do question solving classes, it's always more fun to have more people in the class because it's more interactive. Yeah. So if you wish. Dharun, for inorganic and physical, you can definitely just read the NCERT and start attempting the previous year questions. That's possible for physical and inorganic. For organic, you'll need a little more guidance. It's okay, Johan. Wow, Black Caps has shared it to his teacher. Very nice. If you have any doubts that you want to ask, you can ask me right now. Otherwise, we'll end the session. I just have a 5-minute breather and then I'll go back to Vedantu JEE Hindi channel and start taking a strategy session over there. Hartanam, I have 2 days of rest in front of me, so yeah, it's okay. I can speak for another half an hour, I'm sure. Okay, Johan is asking, I have a doubt. In E2 reaction, would the nucleophile attack if there were two beta carbons? So in that case, you would choose the place which forms the more substituted alkene. Okay, you would form the Sage-Zef product. If this was the case of E2 reaction, pure E2 reaction, then you would choose this instead of this. This and this are both beta carbons, right? So the more substituted one. So you basically have to form the more stable alkene while keeping in mind the anti-periplanar geometry. Okay. Black Caps, I think you have a marathon on Saturday now. I think this Saturday you have a marathon, and on next Saturday also you have a marathon. About Wednesday, I don't think we have a marathon. Baki, the exact schedule will be shared with you on the Telegram group. MGK not necessary, bro. Not necessary for mains. Cis trans EZ isomerism, that's more than enough for mains. Haritaram is asking, how did you manage maths? So yeah, for a fact, my mathematics was not that great when I was preparing for JEE. Neither is it now. I need a calculator for most of my mathematics all the time. So I relied mostly on chapters that are more visual. For instance, straight lines, circles, parabola, hyperbola, all of the conic sections, yeah. Then I relied heavily on vectors, 3D. There were some easier chapters as well, the logical reasoning part, sets, relations and functions, some basic ideas about application of derivatives, you know, the easier parts. So I focused heavily on these areas so that I could perfect them, and the rest of math I could never do. So yeah, the visual parts of mathematics is something that will save you if you are someone who has a natural knack for chemistry rather than mathematics. Cool. Black Caps, you can try to, for sure. If you have questions from E1, E2, SN1, SN2, etc., you can definitely try to do previous year questions on this part. But after the alkyl halides chapter and the revision, you will be you'll be even better equipped to tackle with the questions. Cool. All right, people, I think I'll have to end the session over here. Thank you so much for joining in. Make sure you hit that like button. I'm going to see you sometime next week, and I will let you know of the schedule as soon as I can on the Telegram channel or wherever. See you soon. Take care. Bye bye.